Hi, today's talk is about teaching general relativity, invariant and covariant concepts with balloons and balls, and then leading into my hemispherical relativity pre-Gauss case. Now, this is going to go through some basic atomic modeling and 3D engineering, how shells and subshells work, and also there's going to be a little talk about Bose cylinders, which is the math that makes quantum mechanics and electron subshells work. So the basic frame of reference in physics is quite challenging because you have the basic Cartesian of x, y, and z, where this thing called Pythagoras works, where you can measure the distance of 1, 2, and 3 independently and then use the sum of the squares to determine the distance between them. This is very important because the calculations of your electrostatic charge and all those things is based upon that distance. So if you have x, y, z, then Pythagoras works. However, we have two different systems that also work. We have the overall atomic model, which is sort of a big ball of electrons around a nucleus in the center. Okay? And that is sort of Einstein's relativity. On the other hand, you have these rings, this longitudinal ring, which is called the cylinder surface in Bose proof of quantum mechanics. So when you're talking about quantum mechanics, you have to have cylinders. When you're talking about distances, which is all of our traditional classic one-to-one calculations, you need Pythagoras. And if you need to do relativity, if you need to talk about the curvature, you need spheres. Now, of course, the problem is that when you get to relativity, Einstein threw up his hands and said, well, I can't make this work. So he used an abstract set that he called x0, x1, x2, and x3. x1, 2, 3 being the x, y, z, this one, or the spherical. You see, when you have the radius, that's say nucleus to electron, that's a radial calculation, and we will use that in hemispherical relativity. However, when we're doing the longitudinal rings, the electron subshells, we'll use this green axial force. But that's not in the same direction. That's in the axial direction, rho. So you have a mix of spherical and cylindrical rho. And that's challenging to solve. And general relativity doesn't do that mapping, which I will do at the end here. It doesn't use x, y, z, r, Pythagoras, or even the z, rho, phi, but it uses an arbitrary x1 and x2. Let's see how it works. Einstein's general relativity says that the three basic dimensions work with this x0, which he calls time, or the derivative of time, and that you have a basic set of exchanges where things work out. However, he has four different rules. One is those are general abstract dimensions, and this x0 becomes the transfer mechanism between the other three. You have the ones along the diagonal, which is a special Hamiltonian because it obviously, whatever goes into that stress must come out the other place. So they must have this invisible I potential, invisible for I. And then you also tend to have, per Einstein, that across the diagonal, it becomes the opposite. Think of this as Newton's law of, third law of motion. For every action, there is an equal and opposite reaction. So if I have 1 and 2 in electrostatic, this one pushes away, and that one pushes away, but in exactly the opposite direction. Or if they attract, they both go attracted towards each other. Okay? So, now, so there's a conservation of energy, meaning that these 16 schedules, but again, remember, because of these diagonals, it only has to be 9 in blue. Okay? And some of those could be a 0. And that it has these different things. Now, in Einstein's general relativity, there's a second part, which is that when they do this calculation for these tiny spaces inside an atom, you actually go back to Newton's other thing, which is the gravity constant G. And they use Ricci tensors to actually use that remote planet and star constant to also calculate the curvature, this spherical system here. All right. Now, today I'm going to focus strictly on these two interdimensional relationships. Okay? Invariant, which means that if you move one, nothing happens to another dimension. That's your typical X, Y, Z. Or covariant, where if you move another. All right? That is just like, and I'm going to show you with a balloon. So let's see. All right. So if you take a balloon, and let's say that's going to be a sphere, at this little point on there, you have a distance inward, that's the R. You have the distance going this way or that way along the surface. And for an infinitesimal distance, that's called the math derivative, those are exactly at 90 degrees. It starts to look like old Pythagoras and Cartesian XYZ. However, here's the problem, and this is the most basic thing about relativity. If I'm here, if I make the radius bigger, then this distance here just got bigger. This whole distance. So there's a covariant transfer. However, if I move along the surface, nothing happens to the radius. Okay? And so these two concepts of invariant and covariant are basically two dimensions in a changing system, like a balloon or an electron shell around a nucleus, which is, of course, where we're going to end up. Okay? So now, where do we get that to go? Okay? Well, the real problem is that's only two dimensions. And guess what? We have three dimensions. Hopefully we all know that. So if we move, if we change the radius, this line here goes a little further, then the longitude or inclination, because I always count from the poles, changes distance. And that changes pro rata. The percentage that you change the radius is the percentage that you change that. That's 2 pi r. So since the r changes, the 2 pi r changes. Okay. The same thing goes for latitudes. When you go around these latitudes, if you make the balloon bigger, that changes pro rata. That is the concept of covariant. So everything that comes from the radius direction, I'm going to translate into relativity as covariant. Now, I said also that if you go along the surface, and I'm going to specifically talk about when I go around the latitude. If I go around the latitude, the radius doesn't change, the red here, and the green, oh, the inclination angle doesn't change, so the distance doesn't change. As you move along that surface, there is no change. That is invariant. And a lot closer to what that was XYZ, that works out to get us a working Pythagoras theorem. Now, that surface point right there has our inward distance, inclination direction or longitude, and a latitude direction. And at that one point for an infinitesimal distance, that's the math derivative, that is at 90 degrees. So Einstein said, good, I can use that math derivative and I can get a calculation of how much that XYZ is going to change versus that distance going around the curve. And that's the basic of what you're trying to do in that 4x4 networks. But there's one more thing. There's a third dimension. And that is, if you change longitudes, it's a little different. Now, if you change the longitude, that's still on the surface. The radius does not change, okay? The radius here versus the red doesn't change. However, as you change, it changes by the angle. And so this is by the sine, or for the derivative, the cosine. That cosine variance is the third part, the missing part of general relativity, which we will now make a special case, not the general relativity, but hemispherical relativity that has all three components. And in that way, you get what happens in three other areas. First, you get a cosine, which depends upon the other two things. There's a stress, and that cosine is called a dot product in math, which gives you the cosine in that third direction, which is Gauss's law of magnetism. On the other side, if you go into quantum electrodynamics, QED, you'll find that we need to re-normalize. So if we've done a calculation here, when I move beyond the infinitesimal distance, I need to rescale those three dimensions. So quantum mechanics has a very good procedure. It's a proper procedure, but of course it takes a lot of work because you have to recalculate everything and get everything else around this distance as the normal, the equals 1 versus this distance. So finally, this leads you to this Bose cylinder, the cylinder surface. And that is a model of electron sets where here from the side, you will have electrons that are all attracted to a common axis, but are repelled from each other. So they stay at a distance separated, but in this longitudinal ring. You can see that ring if you look at any electron distribution in your textbook. They are all these sets of rings in one hemisphere and rings in the other. You can also notice that one hemisphere has the extra electrons starting at the exact opposite, 190 degrees relative to the nucleus position. And then you can like layers overlapping them. So you get 2, then 8, but you get another 8. And that is what creates the periodic table, which is the chemistry that runs everything in the world. Now, this is the view from the side. If you look at from that polar angle, just look at that one little slice right there, you'll see these electrons are around a ring. The next layer is an electrons of rings. They have the attractions, the green or orange, towards the axis. And they also have the repulsions to each other, which when you sum all those repulsions up becomes a net repulsion because they're evenly spaced away. So the green and the red hashed offset, but only in this sort of dynamic bumping into each other, quantized electron hemispherical axial plane. All right, so now finally, that gets you to a special case of relativity, my hemispherical 4x4 matrix. Now, instead of calling this x1, x2, x3, and x0 over here, I'm going to put them specifically. The radial dimension, the theta dimension, and the phi dimension. And this is the from, and then those same ones are over here too. So whenever I translate between dimensions, this is what happens. So as I go through the radial dimensions, that first relationship here, okay, is covariant. So that means that as this changes by 1, the change in theta has to have this prorate change in the R, in the radial. Same thing happens, we get a prorate change in the phi direction, in the latitude. And then over here, when I change from latitude to from longitude to latitude, you get a cosine. The cosine of the original theta versus the cosine of the resulting. Darn, that's supposed to be a 1. Sorry, my fault. All right. Anyway, now, there's also 2 other things going to the original status of what he had. He allowed there to be this Hamiltonian, this special relationship here, but I've simplified it. They're all 1s. That means it's flat space and time. Further, this does not transfer across this diagonal. And in fact, the basics of magnetism and creating photons and all the strange things that go on inside those stresses in a molecule, in an atom, is just this one example. There's only one place where the third law of Newton doesn't apply, and that is magnetism, which is that funny shape transferring from radial to the latitudes. So in the end, you get the change of r times the change of delta, that vector, becomes cosine in the phi direction. And this is what's called the left-hand rule, or the right-hand rule, where you're pointing the direction that it's going from the radial. You've got an orientation towards the theta, and guess what? To balance that out, this relativity stretches and it releases only in that latitude direction, which I will discuss more. Thank you very much for your time. I hope this helps you learn and make relativity something understandable for everyone.